All right, perfect. Rohan, absolutely brilliant. To have you here. This topic of robotics and how it connects to sort of like physical AI and the real world is a topic that I've wanted to cover for quite some time. Just haven't really found somebody who can discuss a topic that esoteric and still make it, interesting and engaging. So thanks a lot for volunteering to do this. Why don't we
Yeah,
start?
thank you for having me.
Yes, absolutely. Why don't we start at the very beginning? Could you tell us a little bit about your career journey, some of the different roles you had, and specifically would love to know a little bit more about your interest in robotics and a little bit more background on Figure AI and what the company does and what you do there.
Yeah, so I think I got interested in robotics when even before undergrad, actually, I always had this kind of interest that got peaked when I think Google released their self-driving car, like what used to be Waymo. It used to be a part of Google X at the time. So Google X released their first self-driving car, and that was like my first. I think I was somewhere in like somewhere from eighth grade to 10th grade, something like that. But yeah, I was like, oh, that was my first exposure to a real robot that's like out there, and of course it was very early stages, and now it's like it's been so long now. Waymo has started to operate in the Bay Area and Los Angeles and stuff like that. But yeah, so anyway, I did my undergrad in computer science, and I felt like even then, this was in like 2015, I could see that um, the rise of machine learning was starting to. I felt like it had a lot of use cases within robotics. So I started working in like a robotics lab in undergrad, and I realized that at least at the time, for a lot of these mobile robotics, I was working on robots that move around autonomously. The bottleneck was perception, and the biggest problem that, or the biggest solution that people had for perception was um, machine learning, right? Like just collect lots of data, train stuff on it. Anyway, so yeah, I started working on that. Then I kind of went deeper and deeper into like computer vision, perception. After that, got a job. Actually, even in undergrad, I started like an autonomous driving club in our college, and I think we were perhaps like one of the first people to show like a level 2 autonomy in India, like on an Indian car. So level 2 autonomy is like there are different levels, but it's like adaptive cruise control and lane following, and yeah. And after that, worked in a couple of robotics companies. Um, for agriculture, defense, lots of different applications. And now, yeah, finally ended up at Figure, where, yeah, I think my work currently is training the AI models that help the robots work autonomously. So yeah, that's kind of what I'm working on right now.
Awesome. Thanks a lot, for that background. And we'll talk, of course, a little bit more about what Figure's been doing of late and what's
Yep.
interesting in terms of the work that y'all are doing. But maybe we start off by zooming out a little bit, right? By trying to understand not just what's happening in robotics today, but how things have evolved over the near term, right? And to try and understand what's been happening. Maybe one thing that you could do for us is give us a little bit of a sense, right? Like you spoke about a certain timeline starting back in the 2000s when you mentioned Google X and the self-driving car. But if you walk back even earlier, give us a walkthrough of the timeline, right? Of, on one axis, we were to think about some breakthroughs in robotics innovation or robotics capabilities, and on the other axis, you think of it from a time perspective. What's been happening? Where are we now? Also, in terms of, the holy grail that people are trying to achieve in terms of like, truly autonomous robots, you end up with like iRobot and Terminator and all of that from a slightly sci-fi perspective. But give us a sense, where are we on that timeline? What's happened in the recent past, that's notable, and where might we end up in the near future? Would love to get a sense over there.
Yeah, I think so the in my mind, the way I see it, the fields of AI, which includes like computer vision, natural language processing, and robotics, they have followed a very analogous journey. And what I'll describe for robotics, it's like largely true for computer vision and for natural language processing as well. So I think like robotics started in like 50s, like 1950s, 1960s. It's that old. People made like the first industrial robots. They made robots that you could program in a very limited way. So you could only define some starting positions, ending positions. You would record some trajectory and then just replay that trajectory again, right? So that was like the first robot that could just do work in a repeated way. Then I think in like 70s, 80s was like when classical control techniques were born. So that was when people were like, okay, if I know, like if I want to move the robot in this particular way, if I have a robotic arm, how do I move it? What's the math behind it? And people develop, like now it's standard, it's taught in all robotics courses. It's like forward kinematics, inverse kinematics, things like that, PID controls. It's very standard. So those were developed in like the 70s and 80s. I think in the 1990s is when mobile robotics became popular. So moving away from just rigid, uh, like they're called robot arms are called manipulators in the industry. So like moving away from rigid manipulators to like uh, self-driving. Self-driving is still a big word, but at the time it was more, can you have a robot that perceives the environment around it and figures out how to move. So that was when some other techniques like mapping, simultaneous localization and mapping, SLAM, that's a big area these days. That's when that was born. Autonomous vehicles, I think, came from like a lot of interest from NASA, like space programs. So that was like 1990s. And then 2000s, I think, was when some of those self-driving and things like that actually began to take shape. So there was a big program by DARPA. DARPA is like the US Defense Research Organization, kind
Yep,
of like
yep.
US counterpart of DRDO. So DARPA made this program. I forget what was it called. It was very classic. DARPA Grand Challenge is what it was called. So they had like different universities and research teams and so on compete in like making a car drive itself from, I forget, some large distance. And then they had another challenge, which was the DARPA Urban Challenge, which was like, I think DARPA Grand Challenge was like kind of in an off-road setting, but DARPA Urban Challenge was, okay, how do you make it drive in a car in a city and like follow traffic rules and stuff like that. So that's when that started. Um, um, in parallel in the 2000s, a lot of like early humanoids. I think Boston Dynamics started sometime around then. All these guys started to take shape. Um, and then I think 2010s is when like the first like people started applying machine learning into robotics. So people, because 2012 was like the big breakout moment for deep learning. So people were like, hey, like deep learning is doing so well in like handwritten digit recognition, image classification. So why don't we use it to recognize and parse the environment around a robot? So that's when people started doing that. Reinforcement learning, etc., other techniques like that came into the picture where you could learn things from simulation. And I think like 2016, yeah, so this was like the 2010s, and then now I think 2020s is where we've kind of taken the lesson from ChatGPT, right? Which is that the techniques that made something like ChatGPT work, and again, this is the same in NLP, computer vision, etc., everything, right? Is that all of these fields had very rich histories in the going back to like 50s, as early as 1950s. Um, and I don't want to say like, of course, those techniques are still useful, but people realized that if we can adapt these techniques to build algorithms that get better with data, that gives us a clear strategy to just then it becomes very easy to improve them. It's just like add more data, add more compute, scale everything up.
Yep, yep, yep.
So from the 1950s, so this is true in computer vision, NLP, is that all these classical techniques inspired some machine learning, deep learning based techniques for each of these fields, which kind of were developed in the 2010s. And now in the 2020s, we are in the stage of like, okay, we have the algorithms. Now let's just scale it and see what happens. So I think I find it very interesting that like OpenAI's journey kind of made that possible because
Hmm, hmm.
OpenAI was like, hey, like NLP, we have machine learning is working. Like we have one model for image translation, one model for like emotion recognition, we have one model for whatever. Why don't we just like make a huge model, just train it on as much data as we can get our hands on and see what happens, right? It was a pretty, it sounds obvious now, but it was a pretty revolutionary idea at the time.
Hmm, hmm.
OpenAI seemed like a very risky company, like they were taking a pretty risky bet to make all this infrastructure, collect all this data, spend all this money training these large models. But now, in hindsight, it seems very obvious. And I think that's where like a lot of people, once it happened in LLMs, now it's coming in, like it's already happened in computer vision. People have made like foundational models for vision, which can do like a lot of different tasks, segmentation, object detection, tracking, face recognition, everything can be done by one model. And so naturally, like the next question is, hey, why can't we do this for robotics as well? Because again, we have models that are working individually for individual robots and individual tasks. We've seen that in the 2010s. So now it's like, let's try to do it for, of course, I'm oversimplifying, but like, yeah, that's kind of the plan.
And to the second part of my question, which is if you had to guess or you had to tell us how
Hmm.
close we are to to unlocking the robotics equivalent of AGI, right? Where you have robots living and working alongside human beings in our day-to-day lives.
Yeah.
How far away would you say, if you had to take a punt at what that might look like, how far away would you say we are from where robots become a pervasive part of our everyday reality?
Yeah, I think it's tricky because, I mean, I could be off by orders of magnitude, but just for fun, I think if again, the closest data point I have is like LLMs, right? So if you look at, I think ChatGPT came out in I don't know, like 2022 or something,
Mhm,
2021
mhm,
maybe,
mhm,
I don't know,
mhm.
something like that. And I think it took it's gained a lot of popularity, and I think it happened in like that even that popularity rise happened in 2 to 3 years. I think right now we haven't even seen the GPT-1 moment of robotics. So what I mean by that is GPT, I think GPT-1 was something that could kind of do like a lot of different NLP tasks.
Mhm, mhm.
GPT-2 was slightly better. GPT-3 was something that you could have a conversation with. And then GPT-4 was like almost indistinguishable from a human.
Right,
So
right.
I think in and again there's a lot of engineering and research that went into each, but largely it was basically how do we get more data better and develop better techniques that scale, like improve the model with more data. And I think right now, yeah, we haven't even reached GPT-1. So if you
Mhm,
kind of
mhm, mhm.
look back, um at whenever GPT-1 came out. I don't really know, but it'll take, in my mind, the amount of time it took to go from GPT-1 to GPT-4 or GPT-5, that's the lower bound. Like that, it'll take at least that long to get to like general purpose, like as you said, like iRobot type of a situation. And then you can argue that, hey, robotics involves not just software and AI, but also hardware, right? Which
Right.
is like its own rabbit hole. So it very well could be like twice or thrice that, but I think in my mind it would be, yeah, minimum GPT-1 to GPT-5, however long that took.
Got it. Understood.
Yeah.
That's a super helpful perspective to have, and I think anchoring it with reference to how to think, how we might think about GPT and what it's done on the software side in general, I think is like pretty interesting. Maybe a couple of other questions that I just had in mind to
Yeah.
set the stage a little bit, right, in terms of the landscape. So if you think about robotics from a demand and supply standpoint, right, like on the demand side, the factors that are driving adoption in some sense. And then on the supply side, we're seeing immense investment with companies like Figure AI raising, very, very large sums of money, more than perhaps anyone ever has in the history of robotics as a field. Investors are incredibly exciting. There's a very large number of startups that have popped up and are building. And I think every other week, you see demos of humanoid robots and other forms doing tasks which even 5 years ago would have seemed like absolute like sorcery, right? I remember when I was in college, people were trying to fly drones, they were trying to drive autonomous cars, and none of those things were very good, right? Like they could perform within a narrow range. Even then, they had massive issues on reliability, controllability, and so on and so forth, right? But now it looks like things have changed to a significant extent. So, give me a little bit of a sense on the demand side. Why are people increasingly looking at robots for the home, for the workplace, and so on and so forth? And on the supply side, I know you mentioned a little bit about how figuring out machine learning has really made a difference. But a little bit more broadly, if you have a perspective on how investors, how the broader startup ecosystem, how founders have been thinking, why are people so excited? And why is everyone getting into robotics at this point of time? Would also be helpful to understand.
Yeah, I think I shoot, I forget who was telling me this, but um I think maybe it might have been one of my previous coworkers from China, but he was telling me that um at least the okay, so it's he was saying that China is really interested to make robotics work because they have a huge demographic problem, that their population is getting older and they don't have they don't know what they're going to do. Like I think other countries are kind of maybe relying on immigration to solve that issue, but like China doesn't have a big influx of immigration, so they kind of have to solve it with robotics. Japan is kind of in a similar situation. So in fact, that's why like in the 80s and 90s, like Japan used to be a leader in robotics. It's kind of I mean, it still does good work, but I would like to see it do. I think it's capable of doing much more, but anyway, that's neither here nor there. But yeah, I think that's like a big motivation is just like world demographics and labor shortages. Like a lot of industries are facing labor shortages. Any person you talk to, especially in like blue collar jobs, restaurant workers, factory workers, things like that, they all have problems with um, uh, labor shortages, skilled labor. Um, and I think it's also one of those things that, you know, if at a global level, if like certain countries are investing heavily in these advanced technologies, then to maintain your competitive edge, other countries also need to invest, right? So like Europe has jumped in, the US has jumped in. So yeah, I think it's that's definitely one major part of it. The second, of course, is what I was mentioning, which is like the exponential growth of AI. So people have seen that the I think before it was unclear how to improve robotics. Like as you mentioned, like that, hey, if you're flying a drone or a self-driving car and it fails in certain situations or it doesn't do make the right decision, it wasn't clear how to improve it. Like you could go in and like tweak some rules that okay, in this situation do this, but there are so many endless possible scenarios about edge cases and things, other long tail scenarios. So I think moving to data driven AI kind of gives you a very easy, or not easy, but it's a simple strategy, which is that all you have to do now is like, if you have an algorithm that gets better with data, you just scale your data and compute. And yeah, I think I've also heard a lot of people say that kind of post COVID, they were very afraid by how fragile the global supply chain was. So, or how much we still relied on humans being in physical spaces, right? So when you had this pandemic that was like that kind of wouldn't allow people to be actually close to each other, it just showed that how much if despite all our efforts to digitize and have a digital economy and things like that, it was just still extremely reliant on humans. So I think that's also something that people are like, not, I think it's not a major concern, but it's definitely something that people are starting to think about, right? And then finally, I think um I've also seen a lot of, like in the previous companies that I've worked at, I've seen a lot of new markets open up. So markets that perhaps weren't as big earlier. So for example, at my previous company, it was a startup called Bloomfield, where I worked on robotics for precision agriculture. So that was basically, our customers were like big robotics, or sorry, big agricultural companies that grew, like hundreds or thousands of acres of land. They owned hundreds of thousands of acres of land. They grew a lot of crops, and they were like, hey, we have no idea like what's going on in our field, like which of our crops are working, doing well, which ones are not. Even just like monitoring them takes so much manual, so much manpower. And so we would provide them with solutions where like we would build cameras and things like that that would monitor the entire field and give them like a digital clone that they could just look at on their computer and see that okay, this part of my field is doing well, this part is not, and like I need to allocate, water, fertilizer, whatever. So anyway, that's just one example. There's, so much work going on in healthcare and like surgical robotics, elder care, again, due to like aging demographics. There's like retail, like if you look at, things like drone deliveries, that's actually, that's also something that's driven by consumer demand, right? Like people are like, this wasn't something that I think had a lot of value before, but now people are interested in getting their like Amazon deliveries quickly or groceries delivered quickly, and cheaply. And that's something, like even I saw DoorDash has released like a robot that they've wanna like use to deliver um, people's food, right? And then you have drone delivery, like Amazon has been testing drone deliveries and things like that. Um, and then what else? Yeah, construction. Construction is a big one. People are using like autonomous forklifts and things like that. Mining. So it's just like so many industries, I think, are getting like um they are reaching that point where they could also benefit from physical scale, right? Like how
Got
do
it.
you, if you can
Got
scale
it.
up physical labor. So yeah, and I think maybe one final thing I can think of is governments are also catching up in their regulatory, like they are being more lenient, I think. Like if you just look at even the in the Bay Area, or in the US, the government is giving more, they're willing to work with autonomous driving companies to help them test. to make technology better, but also keep the citizens safe. So I think that's also been another thing which wasn't possible 10
Got it.
years ago.
Got it. Got it. No, I think it's super helpful to think of this, almost in terms of the confluence of like multiple factors that have worked together. We're reaching that sort of like unprecedented labor curve inversion of sorts in society at a time also when these evolutions in machine learning have made a pretty big difference, right? I'm also curious to hear one thing from you. Obviously, apart from the the end product, which is the humanoid robot itself, right? Which is what say y'all are working
Mhm.
on at Figure. Could you give me a very quick sense of what are some of the different areas where you see startups in the ecosystem building? People might be building end products such as yourself. Are they building any sort of infrastructure for robot training and deployment? People working on specific components, like cameras, vision systems, actuators, what have you, right? Just to get a sense of what you're seeing in the valley in terms of where people are focusing on in robotics.
Yeah, I think honestly, it's like it's like what are people not doing in the space, you know? It's
Uh-huh,
so
uh-huh.
it's so crazy right now. Crazy in a good way. Like it's also exciting. So yeah, you have, companies like Figure, which build are fully vertically integrated. So they're building the hardware and software and AI and doing everything in-house. Um, you have companies that are doing individual parts. So you have companies that are, for example, building just the AI, right? So their thesis is that if we just focus on the AI model, if we make it good enough, then eventually it'll work on any hardware that we can deploy it to. It's an ambitious thesis, but it may work. Um, then you have correspondingly people who don't have the AI expertise but do have hardware expertise, so they are building just the hardware. Like Unitree, for example, from China, is builds really good hardware that a lot of people in academia and industry use. Um, Now and then you have, so there's a whole so if you look at like on one extreme, if you say there's Figure which does everything in-house, there's like a whole spectrum of companies that do every conceivable thing. So yeah, as I mentioned, like hardware only, AI only. Then there's also software only. So by software only, I'm distinguishing it from AI, but there are people who are
Mhm.
working on just like how do you build, because software for uh, a robot is a very complicated system which has a lot of sensors, actuators, and processing. It needs to be done like with limited power and things like that. And it needs to be very accurate, but also very efficient. And so there are people specializing in software specifically for robotics. And then there are yeah, people making individual parts like supply chains and things like that. A lot of that is in Asia. And what else? I'm forgetting. Yeah, and then finally you have like the full infrastructure, like the data and software infrastructure. So stuff like, machine learning training and like compute and all that, which is kind of
Got
also
it.
overlaps
Got it.
with AI, as with LLMs and things like that. And these days, I've also found a very interesting group of companies which is providing data services. So, like data curation, collection, labeling, all these kinds of things. And a lot of people are actually collecting vast amounts of data and selling it to other companies as well. So yeah, there's like a lot going on in this space right now.
Got it. Got it. Understood. And we'll come to some of the specific aspects around data, but I think it was great to get this overall sort of like landscape view in terms of what's
Mhm.
happening in robotics. I think what I'd love to now deep dive into a little bit is on the tech side, right? Like a little bit to understand what it is that you do on the day to day and how, these things happen. So one, give us an overall sort of picture. If you had to think about the software or the technology stack when it came to a robot, right? What are the different components, right? You mention things around control, you mention things around perception, you mention things around sensing, right? So if you think of it along these abstractions, what are some of the 4 or 5 buckets that make up an overall architecture for a robot, and how do some of these things interact with each other, would be a good starting point to then move on a little bit into understanding some of the specifics around how you train robots, what role data plays, and so on and so forth.
Yeah, so I think almost any robot that operates autonomously in the world, or in any environment, actually, it could even be a digital environment. I think it has some notion of sensing. So, what information are you getting from from the environment? Is it like images? Is it audio? Is it some kind of force sensor, some kind of tactile, like similar to like human touch and things like that? Then you have some notion of perception, which takes in these raw sensor readings and then build some understanding of, okay, these pixels are uh, a red light on the traffic, on like a road, or these forces mean that I've hit some obstacle or something like that. Then you have I guess you could call it planning, which is that given this semantic information from perception, that okay, these are where the objects are around me, this is where my current state is, that let's say if my current state is that I'm a self-driving car and I'm driving on the road, but I see that there's a red light like 200 meters ahead, then I need to decide what to do, and that's where that logic comes in. And then finally you have like, you could call it control, which is given some command from my brain, like my planner, how do I actually achieve it? So like, how do I actually apply the brake autonomously? How do I accelerate autonomously? And then for a humanoid robot, it could be like, okay, my brain is telling me that I need to pick this up by doing this. So how do I actually like control my fingers, control my hands and legs while making sure I'm stable? So those are kind of, and this is all a very tight loop, that each of these parts talk to each other very at a very high rate, with a very high bandwidth of information, and very very quickly. Like a lot of these controls loops run as high as like 1 kilohertz, so like 1,000 times a second, right? Because like you can just think of, as a human also, like your reaction time is something like, I think like 150 to 200 milliseconds. So similarly, like if you want to build a safe self-driving car, you need similar reaction time, and the way to do that is to like run your um, autonomous thinking very very frequently.
Got it. Got it. Understood. I think that's super helpful. And if you now start getting a little bit into the specifics, right? You we spoke initially about training and what role machine learning has played there. But tell me two things, right? Like one, give us a little bit of a sense of how robots are trained in general and how these approaches have evolved over time, right? Because I remember when I was in college, you used to have stuff like people used to be wearing some patches of sensors on their arm, and they would move it around, and then you would have a robotic manipulator arm that was sort of mimicking that motion and learning, right? Is my earliest experience with seeing how robots are actually being trained. But give us a general view of how robots are trained, and how these approaches have evolved over time. And if you could also double click a little bit into what is it that's happened of late that's sort of allowing this kind of like unprecedented breakthrough, right? You mentioned that, look, applying the same techniques that we've applied to LLMs to robots is what is really allowing this sort of inflection. But what does that mean, to be specific, right? So how are robots trained in general? How have we evolved? And right now, what's changed about the ability to sort of train robots?
Yeah, so I think if to answer the first part of your question, how has robot learning evolved over time? I think initially the very first approaches at at making robots were using some hard-coded rules, right? So again, if you are making a manipulator arm, for example, it could be that if I detect this object, do this. If I feel this force, if you detect this force that you've hit something, do this, and making a set of rules like that. But you can imagine that this works only in very simple scenarios, very controlled situations. Like how what set of rules can you even describe for a self-driving car, right? Like that, there are infinite situations. And in fact, this is not just that nobody has tried. Like I remember when I took my driver's license test in the US. I was reading through the driving manual, and it literally, like, the official driving manual said something like, it's even though this manual is like a collection of rules and regulations, it is impossible to describe or to make rules for every conceivable traffic scenario, something like that. So right, so people have thought about this for a long time, like outside of robotics, and it's just not something that can be done. So that's one thing. So that those approaches worked, but they were very, very limited. Then the second, I think after that, people started working on like um, uh, kind of these uh, applying machine learning in each of these tasks, each of these areas that I mentioned, like sensing, perception, planning, control. People started applying machine learning individually, right? So they said that, okay, let's make a an object detector to figure out what are the objects around me. Then let's make another model it will take all these object detections, and it will decide, okay, what do I do? Like, do I accelerate? Do I decelerate? Do I turn my steering wheel? Stuff like that. And then finally make another model which will actually convert your commands to like actual torques and stuff like that that go into the your motors and things like that. Then this is again like very analogous, right, to computer vision, NLP, where people had different machine learning. Initially, it was all hard coded, then individual machine learning models. Then people were like, okay, why are we doing, like, we are seeing that each of these models are improving with data. So why not just have one giant model that we throw in a lot of data? And that's where we are now, which is that we have, like, a lot of people are betting on like foundational models, like this people if you say that ChatGPT is a foundational model for natural language, or a foundational model for multimodal understanding would be something that you can upload images to and it understands images. So now we're trying to get to um, a foundational model for robotics, which is in many ways a superset of LLMs and vision language models, because it not only needs to understand language instructions and vision, but it also needs to have understanding of actions. So in this, if I see this image, like if I want to pick up a glass in this image, how do I move my hand? How much
Right.
force do I apply? Stuff like that. So it's a strictly harder problem. And yeah, so to answer your question, the second part of your question, I think right now where we are with autonomous robotics, a lot of these a lot of work has gone into having one model do all of the individual pieces that I described. And this isn't specific just to humanoid or these new wave of robotics companies. I think a lot of um, earlier companies, specifically self-driving companies, have already discovered this, that having one model that does the whole thing end to end is better. I think like Tesla gave a talk at a scientific conference where they described that they were doing one full one model for end-to-end driving. I I can't remember if Waymo does that or not, but yeah, there's another company in the UK called Wave. They also do this. So yeah, there's a lot of evidence that this is working well in robotics.
Understood.
Yeah, and so the way I mean, yeah, I can talk a bit more, but yeah, if you about like individual concrete techniques, but yeah, if you have another question, we can put that on hold for a second.
Yep. I think one of the things that I also remember, even when I was in college, that techniques that people were applying to robots in particular was the concept of reinforcement learning, right? And you also see a lot of discussion and commentary around that in the context of LLMs as well. Could you take a couple of minutes, talk to us a little bit about what reinforcement learning is? And what role does it play in robotics? Is it seen as a promising approach? Has it been an integral part of achieving some of these closed loop control systems that you mentioned? Would be helpful to understand.
Yeah, I think so reinforcement learning is basically a particular type of machine learning where and again like machine learning is just like techniques that how do you learn something useful from data, right? Very broadly speaking. And reinforcement learning is a particular subfield of machine learning, which is like you have some data and you are able to um, assign scores to that data. So you
Okay.
you have some autonomous agent, right, interacting with some environment, and you have someone or some entity. It could be a human, it could be another algorithm, which looks at how the agent is behaving and um, gives it some scores that okay, this was good, this was not so good, this was bad, this was very bad, stuff like that, and the agent uses that feedback to get better. And yeah, reinforcement learning has absolutely been very helpful in robotics. The It's been helpful. So I think the main challenge with reinforcement learning is like by definition, it only works when you have a meaningful reward to give your autonomous agent. So in situations where it is easy to define a reward,
Mhm.
reinforcement learning has worked very well. So again, like taking an example from LLMs, if you want your model to solve to play chess, for example, yeah, sorry, not LLMs, but like taking a step back, like before when all these what was uh the I forget, DeepMind had this
Yeah, I think it was
demo, right?
AlphaGo. AlphaGo is the one that you're maybe talking
Correct.
about.
AlphaGo was for Go, yeah.
Yes.
So they used reinforcement learning, and games were a very natural way for reinforcement learning to start because you have a very concrete notion of
Reward
reward.
mechanism. Yes.
Yeah.
Yes.
So that's the first kind of stepping stone that people immediately jumped to with reinforcement learning. I think most of research after that has been how do we define rewards for more complicated tasks that we care about.
I see.
Like in driving, for example, it's been somewhat useful because sure, you can assign negative reward when you have an accident, but positive reward for other cases, but it's like how much positive reward do you define? Like
Hmm.
do
Hmm.
how do you define good driving? Like what if someone accelerates very quickly, brakes very quickly? You want to not reward that, but sometimes you do want to do that. So it's just like
I understand.
making the reward itself is just so complicated. So I think what I've seen in robotics right now is um, the place where reinforcement learning has worked really, really well is control. So what I mean by control is the part that the last part of the stack that I was talking about, which is that if you know what you want to do, how do you actually do it, right? So for a self-driving car, control is actually not very hard, because if you know that, hey, I want to go to this speed and I want to turn at this angle, you just turn your steering wheel to that angle, you hit your accelerator for some amount of time. But for some other complicated, different form factors have much harder control, right? So if you have a robotic arm, for example, control is slightly more complicated, because it's like, if it has, like, if you just look at your hand, right? If you want to pick something up, I actually don't have control on the tip of my fingers. What I do have control of is each individual joint. But the human brain is really good at knowing how do I move each individual joint to move my fingers to where I want to go. And that's something that we have solved also. It's like pretty standard techniques. But what's more complicated now is, let's say you have a humanoid robot, right? And you want it to, let's say you want it to climb stairs.
Right.
Now, while climbing stairs, there will be periods when both of its legs are on the ground. There'll be periods when its right leg is on the ground. There'll be periods when its left leg is on the ground. How do you figure out how to um, rebalance weight across both feet? And then when you step up, the weight should be distributed, like, not just, like, very gradually across, like, individual parts of the feet, of the foot.
Mm-hmm.
How do you move the rest of your body? Like, you'll have to move your hips if you are
Right, right,
move. So it's very, very complicated. But that is something where reinforcement learning has really worked. And there's like a lot of academic research on this, but designing very good, robust controllers is something reinforcement learning has worked in, because it's like, it's relatively easy to define a reward there, right? Your reward is basically, hey, I want the robot to achieve this position of, like, let's say being a ballerina, like, standing up on its toes and raising its hands.
uh-huh,
I
uh-huh.
want the robot to achieve that. So I my reward is how close is the robot to that. And we have simulators which can actually simulate the effect of gravity and friction and stuff like that.
Right.
So you have the robot achieve this position in the simulator, and if it falls, you give it a negative reward. If it stays stable while achieving that position, you give it a positive reward. If it stays upright but it doesn't fully achieve the position, you give it like a medium reward, stuff like that. So that's something that has worked really well, because we know how to define rewards in that. We've come up with good techniques and good
Right.
simulation. That's also one thing that some people miss, is that simulators have come a long way. Um, Simulators have gotten much better, much cheaper, and also it's again one of these virtuous cycles that, like, other advances in AI have also made simulation better, because with all this GPU computing and stuff like that, a lot of simulations actually used to be very slow, but people have now implemented simulation algorithms that run really, really efficiently on GPUs. So stuff that would take like minutes to simulate before is now like you can run it in a few seconds on GPU. So now you
Got
can
it.
do like real-time simulation and things
Hmm.
like that.
Hmm.
So yeah, I think short answer is reinforcement learning has worked very well there, but I think there's still some work to be done to make reinforcement learning work for to solve the other parts of the stack that I was talking about, which is like perception or planning. Because it's like, if you want your if you want your robot to pick up an object on the table, it's like there are so many things it can do
Right.
in that. And then how do you even decide, like, how do you even give it a reward? How do you even detect that it has picked up the object? And then when do you give it a reward? What if it picks it up in an unstable way? What if it picks up while, yeah, it's again, it's like self-driving, where defining a reward is very difficult. So that's, I think, something that work needs to be done.
That's actually super interesting. I'd honestly never thought of it from that perspective, right? I think what had always been sort of more on my mind was the whole mechanism through which it understands, and then it changes and tries in a different way depending on what the reward mechanism is. But I never gave much thought to how difficult it is to even design the reward mechanisms, right? That there's a lot of modeling work that's
Exactly.
going on apart from the problem solving itself, which is happening. Was like a really, really interesting take to have. Along the lines of what you were just
Oh,
mentioning. Yeah,
sorry to interrupt. Actually, when you mentioned, I forgot to mention one important point also is
please go ahead.
when apart the reward is one of the most important things, and then the other thing is also the ability to interact with the environment, because you can only grade something, you can only grade performance when you actually see the agent do something, right?
Right, and measure it,
So
right, in some
yeah,
metrics.
exactly. So now that acting can either happen in the real world, but that's obviously dangerous. Like if you have a self-driving car that you're trying out in the real world, like it could do unsafe things, so you don't want to
Right,
test it in the real world. So then you are like, okay, let me test it in simulation, but then obviously your simulator is not perfect. There's like a simulation to real gap. Um, then it's also, you also want an algorithm that learns with that doesn't take too long to learn, so it doesn't require too much data.
right.
Otherwise you'll just be interacting with the world, and the model will just keep improving very slowly. So those are yeah, answer is like interaction with the world is again something that is a bottleneck, and that's again
Right.
something that either simulation can solve, or if not simulation, you have to do it in the real world, but then you have to do it efficiently, because you can't you might have heard these figures that some people say that, oh, we trained our algorithm for like a million years or something worth of data in this in simulation. Like,
Right.
sure, if that works for you, that's great. But if you don't have an accurate enough simulator, then like you can play chess in a simulator, but you can't really drive a car in
Sure,
simulation
sure, sure,
accurately.
sure.
So if you apply the same techniques, you'll just never be able to learn. So yeah.
I I
Anyway, that's yeah.
I think that makes a lot of sense, right? Like it's like data becomes like absolutely like incredibly important here because it's pretty much garbage in, garbage out. Otherwise, right? One of the things that I also wanted to talk about a little bit, and you alluded to it right at the beginning when you mentioned foundational models, and then what you just mentioned before this, right? Which is in terms of being able to abstract the real world well enough to be able to train models and run simulations is something that I want to double click, right? So I think data in particular as a building block is something that I remember always being a challenge, right? In robot training, you have a lot of these platforms. You have NVIDIA with like Isaac Sim, and I think recently they launched something for self-driving called Alpamayo, and their entire effort is, look, how do we actually like abstract the real world? How do we like provide all this like data for physical AI development, which is supposed to be very different, right? I remember when I was starting my first job, I was at a razor blade factory working for P&G, and we were trying to implement um, certain like vision systems to detect defects in razor blade packaging, right? And in another factory, we were trying to like detect any physical damage to the edge of a razor blade after it's been sharpened in a very high speed line, right? These are like lines processing, I think on the lower end, 300 razor blades per minute, at the upper end, 900 razor blades per minute. So it's milliseconds of operation that's happening at every stage of the machine. And it was just impossible, right? Because you had to teach the algorithms back in 2019, 2020, what each individual defect look like, right? Like this is a corner folding, this is a tear, this is an incorrect gluing, right? And so on and so forth. And it became like a nightmare to be able to generate enough quantities of defects, to be able to train the model to understand what is bad quality product and reject it, such that I think the savings that we would get from the machine's uptime improving were completely eroded by the amount of product that had to be wasted to collect enough images to be able to train a functional machine learning model, right? And at that time, this only went so far. Today I understand that in a lot of places where I had seen people implementing these techniques, there are like actual like production scale live solutions, right, that are being able to detect defects in milliseconds, microseconds, and like reject the bad product physically from the machine, right? And similarly on the humanoid robotic side, or what I see folks who I know working in with the warehousing side and material handling, their robots are being able to achieve like millimeter precision in going in, picking up a pallet or picking and placing things and so on and so forth, right? So I want to understand what has become different, what is changing, right, from a data availability, from a data infrastructure perspective. How close, do you think we actually are to achieving that sort of holy grail of endless, completely realistic, synthetic, and like simulated data? But that data bottleneck or that real world or that sim to real gap that you were mentioning, how broad is that gap today and how fast is it diminishing?
Yeah, so there are actually multiple facets to this. So I think firstly, if you talk about endless synthetic data, I think we, arguably speaking, we already have that. If you, with the caveat that it's all endless simulated data, but it's not accurate, right? So, with varying levels of accuracy, I guess. Uh, and by accuracy here, I mean like how realistic is it? How close is it to the real world? So one thing that some people have done is that they're like, hey, look, we don't know the exact, for example, like friction coefficients of the real world in every possible environment. We don't know, like, there are different physical parameters, like, coefficient of restitution, things like that. We don't know all of those in the real world, right? We don't have all the dynamics, right? But what some people say is that, hey, if we train our model in simulation and we train it on so much data with randomized physical coefficients, right? So we randomize, like sometimes we give it a slope, sometimes we give it varying terrain, sometimes we give it, like, if we're talking about, let's take an example of teaching a humanoid robot how to walk, right? So it's like, if we or teaching a some other like four-legged robot dog to navigate something, it's like you can randomize your floor alone in so many ways: terrain, friction, how slippery it is, etc., etc. That um, the hope is that if you randomize it enough, the real world, like if your randomized space is like some spectrum, the real world will always lie within that spectrum, is the hope,
That's
right? So
deep.
like if you
That's deep.
go if you go to some carpeted floor, it'll be at one point in the spectrum. If you go on a tiled floor, it'll be at another point in the spectrum. But the hope is that with enough data, you would have um seen the real world, enough of the real world at different points in the spectrum.
And
So
one question just to jump in here,
mhm,
because I'm super curious about this. But how do you know, right? Like if you can generate every possible variation
mhm,
of reality using physics, right?
mhm,
And the good part is that the real world is within this superset somewhere. But you
mhm,
want to train the model on the real world, right? In some
mhm.
sense, you don't want it to learn physics which are irrelevant, like which are unrealistic or incorrect in
Yeah.
some shape or form, right? So how do you weed out what is actually real from like a billion, trillion, quadrillion different things that you could simulate? I was just on that point, I was just curious.
Yeah, I no, that's a good question. I think uh the way we usually do it is that is not necessary. Like, short answer is we can't weed out, basically, because The problem is that we don't know exactly which parameters are closest to the real world. So we actually don't know. But the good news is that what we do is we make the model perform well in all of those scenarios. So we
I
train
see.
it to perform well in situations which may not be super realistic. Um, but the hope is that if we give it enough data, and this is what people have observed, is that you give it enough data, the model actually see the model is we tend to like humanize the model by saying like, oh, the model learns this and learns that. It's just a
Mhm.
mathematical mapping, right? It picks up patterns from the data based on the objective that you're training it for. So when you give it a lot of data from a lot of different very diverse data, what happens is you remove any other spurious correlations
I see.
that might be in the data. So the only possible thing that the data can so that the model can learn is the real way to solve the problem, which is that
I see.
okay, if I need to step in this way, I mean, a simple example from like image classification is like, people have observed that with if you train a model on very small data sets, then your model overfits, right?
Right, right.
What overfitting means is that it learns some pattern which is present in your training set, but it's not a real pattern
I
that
see.
exists
I
in the
see.
real world. So it could be, for example, that in your handwritten data set, yeah, whenever you wrote the number 9, some pixels in some particular spot were like there was some noise there or something like that, right? And that's what the model learned. But if you collect like a million or a billion such images, then all such noise disappears over time, because it becomes much more representative of the real, like, images of digits or whatever that you see, or
Right,
letters that you see in the
right.
real world. And um, at that scale, those noise effects tend to average out. And it's the same thing with this domain of randomization that I'm
I
talking
see.
about, which is
I
that
see.
the more you randomize, the more these spurious effects will kind of average out, and you'll force the model to learn what's actually needed to solve the problem. And yeah, this is like kind of this is only step one, I think, in like the what you mentioned about like having endless simulated data.
Synthetic data.
Step
Yeah.
two is like we can make simulated data more realistic. So especially I talked about like randomizing environments. We can't really do that with images, right? Because if you look at images, if you just count like in a 300 by 300 image, there are so many possibilities of pixels. Like, each pixel has 256 values, or 256 to the power of 27. It's like some
It's an
astronomical
absurdly,
number.
absurdly large number. Yes.
Right. So it's not possible to do this for images. So for images, what we do is what you were alluding to, which is we have to weed out non-realistic images. There are lots of different techniques to do that. Generative AI, generative vision models have become a long
Mhm,
way.
mhm,
So
mhm.
they can help you either convert. There are a lot of simulators which render images for you, which are kind of like have realistic physics, but not very realistic appearance. So you have models that can convert them to more realistic looking images. There are models that do physics and video together. So all of that is also like, exploding very, very quickly, like with things like Sora and all these video generation models. So that's the second thing is that we are, I think, in the image space. So on the physics space, you can just randomize everything. In the image space, you can now convert uh, uh, rendered, like, not realistic looking simulated images to very realistic looking images.
Right, right.
And I think the way that the most robot learning companies see data now is what we've it's a pyramid. So what I mean by that is data for, and again, this is very similar to LLM pre-training and stuff like that. So for LLM pre-training, what people have found is that, hey, when you pre-train a model from scratch, you just train it on all kinds of data you can get your hands on. So just scrape the internet, just throw in everything that, well, I mean, not everything, but like they still do have some quality checks, but really it's like all as diverse data that you can get your hands on, different languages, different genres, etc., etc. Then the next level is, okay, what people often call SFT, supervised fine tuning, but it's
Right.
basically now we focus on very highly curated, very small data sets, like very, very high quality code, for example, for code generation models, or very,
Mhm.
very high quality essays, or very, very high quality question and answering, and things like that. And then we post train this large model on these very small data sets, so that it still remembers the semantics and language and knowledge about the world that it learned from pre-training, but it also it becomes very targeted in its output.
Right. Right.
And then
Right.
finally, they do like some RL to kind of push it from. So the way I think you can think about it is like very, very roughly speaking, these aren't
Yes.
real numbers, but like pre-training gets you from 0 to 50.
Uh-huh.
Supervised fine-tuning gets you from 50 to 80 or 90. And um, uh, what do you say? RL, like RLHF and all these things get you from 80 or 90 to 100. And it's very similar in robotics now. So, but I think the biggest question on everyone's mind is we don't know what that pyramid looks like for
I see.
robot learning.
I see.
But roughly speaking, and this is kind of, there's a lot of consensus around this. Most people view like random in the wild videos, like random YouTube videos, make up the bottom of the pyramid, right? They're most easily available, very cheap, but very low quality. Like it could be anything. It could be people like us, like talking. It could be like people actually interacting with the world. Some of that is more valuable than others. Not all of that
Sure.
data is valuable. So figuring out, so that's why it's the bottom of the pyramid. And then top of the pyramid is probably what you were describing, which is, it's called teleoperation, which is that someone like wears a suit or a glove, and whatever they do, the robot mimics their movement. So that's like the gold standard, right? Like if you could have a human do that in like all possible situations, and we collected a massive like internet scale data set of that, like we would be done. So, but it's obviously very expensive to collect. You need a lot of robots, a lot of humans. So that's why it's like at the top of the pyramid.
One
Very high.
one one sidebar here, just curious.
Mm-hmm.
Given that, practically everyone's carrying a mobile phone these days, or
Mm-hmm.
they're wearing wearables or smartwatches at any given point of
Yep.
time, and most of these devices, if not all of them, have some form of accelerometer, some form
Yeah.
of controls that help you understand space, time, velocity, and so on and so forth, right?
Yep.
Because your Apple Watch just automatically pings you and says, "Hey, are you going for a walk?" or "Hey, I think you're cycling," and so on and so forth, right? And I think that's a combination of one, speed, and second, the motion or the path that your wrist, which is where the watch is taking, right? It's different when you're cycling, it's different when you're walking, different when you're running. Just curious to know, has anybody tried to try and collect, this sort of physics data from wearables, smartwatches, etc., to try and train robots? I mean, I would imagine that someone like Apple probably wouldn't give you that data. They'd in fact use it internally for any robotics development that they wanted to do. But if you take any of the others, right, or you even take a smartphone manufacturer, because they have an accelerometer on it, right, and you can still at least, I don't know, count steps, etc., on your phone, even if it's in your pocket. So just trying to get a sense, has anybody collected this form of data, tried to collect this form of data to help train models? It's a very random question from my side, but it just struck me while you were talking about this.
Yeah, I think I don't know off the top of my head if anyone has tried collecting this data. I'm sure all the wearable companies are recording as much of and keeping as much of the data as they can.
Right.
I I'm trying to think. I don't I think people have tried to use that data to do things like localization, like figure out where you are and
I
stuff
see.
like that. Like I've heard of random research that has tried to like even do things like so you know your phone can give you a GPS signal so you know where that person is, but GPS has some accuracy. I forget. I think it's like maybe something like 10 meters or something. I forget
Uh-huh, uh-huh.
exactly how much it is, but um, people have done stuff like using like the strength of your Wi-Fi connection and the accelerometer and other IMU readings and things like that from your phone to get very precise locations of like up to a few centimeters of where you are in your house, right? So I mean, they're kind of privacy evading perhaps, but yeah, so there's been stuff like that. I think the value of I haven't seen a lot of people use or think about using that data for robotics. Um, I'll have to think a bit more. I can't say for sure if it's
Sure,
useful or not useful,
sure.
but I think the main problem is that it's again goes back to that kind of data will give you physics information, sure, but physics is something that's like low dimensional and easy to optimize, right? Sorry, not easy to optimize. I mean easy to explore or easy to sample from,
Hmm.
whereas or easy to randomize. Whereas images is actually the harder part. That's harder to optimize, harder to randomize and collect a lot of variety. So I think um, this large scale data collection is something that um, is most useful for number one, images, and number two, actions. So very, very fine grained actions. The problem I think
Understood.
with like wearables and stuff like that, maybe at some point smartwatches and maybe VR goggles, VR headsets might give us that, but if we could get really accurate action information, so like
Uh-huh,
when you
uh-huh.
pick up a phone, how exactly do you position your fingers, how much force do you apply, stuff like that. That's something you wouldn't really get it with a smartwatch or your smartphone.
Sure,
But
sure.
maybe if eventually enough people start using VR headsets, then and your hands are visible, then that's
Right.
something we can capture,
That could
right?
be very, very
Yeah.
good. Got it.
But that's exactly those are the kinds of questions that we are trying to ask right now is what are what are the different, like it's a very creative space. It's a very creative time where people are trying to figure out, hey, like what are the different points in the pyramid, right? So as I was saying, like bottom of the pyramid is videos, random YouTube videos. Top of the pyramid is teleoperation, and then in the middle you have so many different things. Like you have egocentric video, which is like literally someone wearing a VR headset doing some actions. So you have
Right.
video from their point of view
Point
with
of
their
view. First person
um
view.
exactly with their and you can look at their fingers and hands and infer what actions they are doing, but you don't have any force information. Then there are some companies doing in the industry, it's called UMI
Okay.
hand. I forget what does it stand for. Let me look this up. UMI. Um, I think universal manipulation interface. That's right. So basically, it's a fancy term, but basically what it means is you you create like whatever your robot hand is, you create a replica of that hand and you make it like a glove, right? And then you use that glove to like when the humans are out there collecting, excuse me, collecting some data, you actually go out there and like collect data with that glove. And the advantage of doing that with as opposed to using a human hand is that your robot's hand is obviously different from your
Sure.
human hand. It has different like degrees of freedom, how much you can move and stuff like that.
Right.
So if you get the information of your robot hand doing it, then it's much more representative of what you'll actually run on the robot.
Sure.
So that's like higher up on the pyramid. But then
Plus,
it's it's
you can get force and pressure data as well,
exactly,
because you can have sensors on the view.
exactly. Yeah,
So
so that's again higher up on the pyramid, but again, it's like more expensive than YouTube data, obviously,
sure.
or it's more expensive than egocentric videos also because you actually need to make these sensors and hardware and give it to people. But yeah, there's like so much uh, space in this pyramid. Like, people are spending a lot of time coming up with creative trade-offs, which are
Interesting.
cheap,
Very interesting.
scalable. Um, so yeah, I think the answer to your main question is endless simulated data. I think in a sense, we are there.
Hmm. Hmm.
Can endless simulated realistic data? I don't think we are there.
Yes.
But I think this it seems like, yeah, not a lot of people are betting on getting endless realistic simulated data, but people do seem to be betting a lot on this pyramid approach,
Sure. Sure.
which again, we don't know if it'll work, but there seems to be enough evidence that it is scaling up. But maybe if this doesn't end up working, then yeah, I could see people working, going back to like uh, endless simulated realistic data.
Understood. Understood. And maybe just one last question here. Do we
Mhm.
have the equivalent of a scale AI or a Mercor for robotics? Is that something that you've seen? Like, are there companies that have offices full of people wearing those gloves, touching everything from grass to something delicate like an egg, right? Or doing fine tasks like trying to thread a needle and so on and so forth, or handle a screwdriver, right? Is that a thing that you've seen, become a part of the training infrastructure and training capabilities?
Yeah, I think a lot of these, like I know Scale AI, and a lot of these companies that have data operations already, they are trying to kind of also get into robotics. Um, I don't think there's any big established players yet. Because the issue also is that, or the challenge is that a lot of these needs are still very niche, or still used to be niche. They're getting more standardized now. So most robotics companies actually would end up collecting and annotating and building all this infra themselves. So that's what Figure does. That's what a lot of other companies also do. Um, Rather, most other robotics companies still do. But I've seen recently, as I was kind of alluding to this earlier when I said that, there's like in every conceivable space, there are in this whole robotics ecosystem, there are companies popping up. So one company, or one type of company I've seen, um, is people they ship these like cameras or VR headsets and stuff like that to lower income regions, like especially in Asia, and they have people collect a lot of data, just like doing some kind of factory work or manual work, like folding clothes and things like that, and they sell this data at pretty high margins to robotics companies and in like Silicon Valley or elsewhere. And um again, like that's just one example, but there is like just collecting that data and then like doing quality checks, diversity checks, labeling services. I think, yeah, the market is very fragmented, is what I'll say. Like there's no, even in the LLM space, from what I'm not very familiar with the LLM space, but from what I've heard, it Scale AI, of course, is a major player, but even there, I think the market is quite fragmented from what I've heard. But in robotics, it's extremely fragmented right now, and I think part of the reason is just like a lot of the needs used to be niche, but
Right.
if and when this pyramid gets like standardized,
Uh-huh.
then
Uh-huh.
we could see more and more players emerging. But
Very
but
true.
for now, it's still very fragmented and very lot of in-house solutions and stuff like that.
Got it. Got it. And maybe now just moving on to the last part of the conversation, right? Would love to know a little bit more about Figure in particular, right? I think the chief sort of question that I have is why the focus on a humanoid multi-purpose robot as the form factor, right? I've heard arguments from a lot of other folks also who say the opposite, which is that look, robots while you can generalize how they sort of do things, the tasks are still at times very specific. It's a very 80-20 in terms of 20% of form factors will take care of 80% of the tasks that are potentially out there. So it's not even that you have to build an infinite number of variations. You can build like 10, 20 variations and it'll take care of like most everything. And it's better to do it this way because then each individual task is done to the highest fidelity possible, right? But of course, y'all, Tesla, right? I think to a lesser extent, the folks at Amazon, and then of course, Boston Dynamics as a player who's been around for a while, have all taken that approach that, no, we'll build humanoids. We like the humanoid form factor. And I think Figure in its recent demos that I think I saw on YouTube, I think there was a video of a robot loading and unloading a dishwasher and a bunch of things, right? Which is very complex, high fidelity tasks involving a lot of like interactions with a dynamic environment, right? Like opening a dishwasher, handling a fragile like glass vessel, putting it in, and all of that. So clearly, it's working. What you all are doing, right? So maybe couple of questions, just to like sort of talk about all of this together. One, why does or did rather Figure focus on humanoid robots as its form factor? Number one. Number two, what's worked for y'all, right? What's been different? What's been the insight that the team has had, which has allowed y'all to get to this sort of unprecedented success? Would love to understand. So why this strategy, and how have y'all made it work? What's been different? What's been interesting about what you've seen at Figure?
Yeah, I think as to why the humanoid form factor, so obviously I can't speak to the exact what's the reason the company is focusing on it, but my personal view on it is as to why it makes sense. Um, I see it from two perspectives. One is the technical perspective, and then one is kind of like the thinking from first principles, I guess. So if you think from, let's look at the second one first. So thinking from first principles, you know, you can in the limit, like in imagining setting all technical issues aside, like if and when we do get to general robotics, right, that we can make robots work almost as effectively as humans, let's say. I think in the limit, the humanoid form factor is probably the one that makes the most sense. And the reason is that the world already is built for humans, right? So we have like, if you just look around you, like all the objects are made such that humans can grasp them. Doorknobs and door handles and everything exists, like stairs exist because they're all optimized for um, a self-balancing bipedal two-handed 10-fingered entity, right? um and then the other thing is this is kind of more philosophical. I haven't thought too much about this, but I think that the reason that humans even evolved with this particular form factor, I think, is a reason that this was perhaps one of the more optimal form factors for the environment, or this environment that we live in. And um the thing that I find very interesting, again, like this is speaking in the limit that if and when we get to general robotics, that you could argue that, hey, like I could have a wheeled robot which is like doesn't need to constantly balance itself. I could have like a 10 armed robot. I could have this or that. The issue is, I think, if you have a humanoid, that's something that can leverage all the same tools that humans have built. So for example, if you want your humanoid robot to climb, like get something from like a high shelf on the kitchen, it can use the same step tool that a human uses, right? So you can like drag that stool, place it on the ground, step on it, open a cabinet, pick something up and hand it to you. It can um uh crawl under a car to help repair it. It could again, like this is we're talking about in the limit. So I do think that for that reason, the humanoid form factor does make a lot of sense.
Understood. Understood.
Of course, we're not there yet. So, from a more practical perspective, the main advantage I see of a humanoid right now is that I've worked in robotics for a while, and I've seen that. So I'll give you an example. If you look at a manipulator arm, right, like an industrial arm that a lot of factories use, the if you look at the cost that goes into deploying that arm, the cost of the arm itself is like 20% of the total cost. The remaining 80% of the cost comes from actually setting up an environment around the robot. So
Right.
setting up the base, setting up the like safety enclosure around it and things like that. And even if you want to move that arm like 100 meters, 200 meters to a different site, you don't have to pay that 20% cost because you've already purchased the arm, but you still have to pay that 80% cost again just to move it by 100, 200 meters. I don't see that problem with humanoids.
Right.
If you have a
Right.
humanoid in a factory, which is like helping you load a truck, you can, within the same span of a few minutes, you can have it walk over to another site and help you with another task. You can have it bend down and help you um, load a washing machine. It can use a steps tool to go. It can use a ladder perhaps to like climb something. It can walk upstairs or take an elevator to go on a different floor. So yeah, practically speaking, and these are things that we're getting very close to all, or like these are already things that humanoids can do. So I think I already see a very real value proposition for humanoids, personally speaking. And then finally, from the technical side, I think this isn't something I've heard a lot of people say, but I think it often uh, ends up getting missed, but it's very important, is that it's very the humanoid form factor is the most optimal form factor to learn from humans. And
Mm,
we have a lot
mm,
of data from
mm.
humans. So we have YouTube videos from humans, people interacting with
Right.
two hands
Right.
and 10
Right.
fingers.
Right.
We have, like, again, teleoperation is easy to do because we have two hands and 10 fingers. And yeah, all of these things. So, if you have a 10-armed robot or a wheeled robot, those kinds of you lose the advantage of that data. Um, yeah, so that's kind of the way I see it, is like, philosophically,
Got it.
uh,
Got
I
it.
and then practically and then technically, it seems like humanoids seem to be the most optimal form factor as
Sure.
of today.
Sure. Sure. I think that's a super interesting. And it's like quite enriching also the way that the way in multiple levels that you think about it. I also believe some of this perspective on specialization that people have, right, perhaps comes more from a machine understanding of the world. Like if you think about machines that make stuff, everything, right, from food to medicines to metalworking and whatever. we have very specific machine designs that do very specific things, right? For example, when I used to work in Gillette, which P&G in the razor blade factory, the core design of the machine that makes razor blades, or a machine that packs individual razor blades into wax paper, right? Or then packs stacks of packed blades into a box, right? And then you have a pack of like 10 razor blades and so on and so forth. These machines, in many ways, their core mechanism, or the transformations that they have to make, which is picking something up, putting it somewhere, turning it in some way, pressing it with something, these for different products that we've learned to make over time have become very distinct, right? Like a razor blade packaging machine can do a few narrow tasks which are in and around that particular task of razor blade packaging, right? For example, a machine that can fill sachets, right? It can fill different kinds of sachets. It can fill tomato ketchup. It can fill shampoo or conditioner, right? It could potentially fill something larger, which is hand wash, right? Different viscosity, different volumes, but the action is still essentially the same, right? You have two pieces of packaging material which are coming in like this. They're getting sealed at the bottom. They're getting filled from the top and sealed at the top, right? Again and again. So I think because people tend to often think about mechanical processes or like these sort of machine operations in terms of the transformations, that okay, what are the different tasks or the different changes that you have to take a particular raw material, pack material, all of these things through and manipulate them to be able to get a finished product. And because those have become so specific, like I think a razor blade packaging machine hasn't changed in its core design in 100 years since King Gillette started automating how any of this happens. I think we've taken that approach a little bit also to how we think about the ultimate machine, which here is a multi-purpose humanoid robot, right? Which could do these things. Because I think if you ask somebody to think about a universal machine which could make everything from razor blades to packets of chips, they would find it impossible, right, to hypothesize how a machine could be that generalizable, how it could change its effectiveness and form factors. But I think with a robot it's different, right? The robot doesn't need to change anything because as you said, right, the human form factor is already designed to handle a very large range of diverse tasks with a decent enough degree of effectiveness, right? Such that it can work. So I think that's super interesting. Last question before we sign off for today: what's new? What's interesting? In terms of the work that Figure is doing. Any insights? Anything you can share that is already public in terms of a little bit about what's also happened that's helped you all get this sort of breakthrough with your humanoid form factor.
Yeah, I think I think Figure is kind of in a unique position of having a very singular focus on solving like general robotics, right? So I think let's see. So one I think is I think it's just how in this space, there are so many different things you can do and try. I think the more focused you are, the more effectively you can use your resources. And I think that's something that has distinguished Figure because Figure has a focus on humanoids, right? Like it of course, like some people can debate, hey, like is humanoid right or wrong? And sure, like maybe like, nobody knows the correct answer as of today, but you still have to make a bet as of today. Like what are you going to do, right? Are you going to do a humanoid? Are you going to do something else? So I think Figure has a very clear focus that we are going to do humanoids. Um, so that removes a lot of uncertainty about like changing, like, hey, you don't second guess yourself. You're logged in. You're like, we're going to do humanoid. So then you figure out, how do I solve this problem? rather than keep second guessing the form factor. Number two, I think, is again having a singular focus to making like being fully vertically integrated. So having like building hardware and software. A lot of companies uh, in um, robotics try to position themselves as software only plays or AI only plays. And there are different reasons as to why. Um, I think one reason is that it's easier to raise money if you're doing only software because hardware is hard. It takes capex, it takes a lot of time. It takes you have to deal with manufacturing and supply chains and stuff like that. Whereas as software doesn't have any of those issues, so it's easier to raise money. It simplifies your problem also, like your again just technically speaking. Um, but I think in a complicated problem like robotics, where if you don't have control over your sensors, your onboard computers, your actuators, then I think you're just you 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 don't have control over such an important part of the whole system. So in my like I don't or I don't think that you can optimize this whole system while keeping such a massive part constant or frozen, right? You have to optimize all of them in parallel. So you have to iterate over your hardware and see, oh, hey, this is making like this. If the hardware was so and so, it would make it easier for my AI model to perform autonomously or to learn this task properly. If it had these sensors, this would be valuable. If the fingers moved in this way, this would be so that hardware, software, AI co-design is very valuable. And I think very few people have that right now because they've made like individual bets on just hardware or just software or just AI. And yeah, I think another thing that's again like just being focused is that I think Figure's focus is to have a product, right? Like a humanoid robot product. Like it's not, um, there have been a lot of robotics companies around which have um, they've kind of build like done research for researchers' sake, which is valuable. Like research is valuable, of course, but I think what what I like about Figure is that a lot it we do a lot of research, but it's all for the eventual goal of making a better product or like making a better humanoid or like making the humanoid do better things. And so it's because once you start doing research, it's very easy to get lost in like the academia, land of academia, like ideas and stuff, because it is very interesting. But you have to, if you don't have that thing to ground yourself, like it's you forget why you're doing this and you get into just trying out a bunch of different things. So I think that focus is again like it just helps us um be more focused. So yeah, I think to me it's like all about in this space, how focused are you, how much can you reduce your search space, like what
Uh-huh, uh-huh.
we're just doing this one thing, human general purpose humanoids, and not dealing with any other thing.
Got it. Got it. Uh, Rohan, this was absolutely, it was absolutely fantastic speaking to you. I think this topic and this discussion has been like extremely enriching from a technical perspective, from a philosophical perspective, and it's very clear that you're someone who's incredibly passionate about robotics, and it comes through in the conversation. In fact, I actually think this might be the longest podcast that we've ever recorded
Oh,
at, uh,
okay.
at Ops Matters, which is always a great sign. So once again, thank you so much for having taken out the time to do this.
Of
Really,
course.
really appreciate this, and have a great rest of your day.
Yeah, thank you very much for having me. And yeah, it's funny you mentioned this is a long. Felt like I had to control myself to I can talk much more. So, but yeah, thank you very much for having me.
Perfect. Thank you so much, Rohan. Take care. Bye bye.
Bye.